Hello, I'm Paul Beckwith, and this is not Shackleton the Explorer. This is Sally. I'll have to think of a good acronym for Sally that is climate related. So, anyway, Sally is, I think, half the time the cats are fed that she goes and steals Shackleton's food. So, I'll have to keep a close eye on them because they seem to be. I thought they were eating the same amount, and Shackleton is a very thin cat, and Sally's needs to lose a bit of weight. But anyway, I'm going to continue this video on the same vein as my last two videos. I'm talking about the BAMS report, Bulletin of the American Meteorological Society. The title of the report is State of the Climate in 2012. Just Google that and BAMS and you'll find the report. You can download a high-resolution version of the PDF, and it's chock full of climate information on the climate in 2020 relative to the previous 3 decades. Most of the baselines, I should point out, in this report are 1981 to 2010. So when you look at the temperature rises, etc., you have to be very careful. It's not relative to the turn of the century or to pre-industrial. So I'm going to focus on a lot of the figures and maps as I just continue to go through this report. And my cat really wants to get down, and she's shedding like crazy. Okay, so here we have the, this is the, there's a bunch of maps here. We have the global surface temperature in 2020, and these are anomalies relative to the 1981 to 2010 time frame. And the reason why they use this, meteorologists like using this as a baseline. They call it the climatological. They refer to it as climatological, right? And it's a 30-year period, 30-year average, but it goes to the but it's very recent, right? There's been an awful lot of climate change that has occurred in this time period. So if you really want to see what's happened, longer term, you need to look at the, say, 1880 to 1910 baseline, or even the 1750 pre-industrial period, the original definition of pre-industrial. So this is surface temperature anomalies. So this is 2020 relative to this baseline. And you can see the regions where we have the most warming, no surprise, up in Europe and in northern Russia, Siberia, also in the U.S. Southwest, and areas in the Pacific Ocean. Remember, we had marine heat waves over here. And okay, so those are the key points. Some of the cooler areas, we've got this global warming hole, which shows up south of Greenland. I believe this is happening because the Gulf Stream, as it comes up, it's not going as far over and as far north as it used to. So there's a cold anomaly there, and there's a warm anomaly here. These are lake temperatures. These are anomalies. This is from 1996 to 2016. Okay, so even more recent baseline. And you can see that the lakes that are really getting the warming, have the real temperature warming anomalies, they coincide to a lot of the regions where we had very, very high temperature anomalies at the surface. No surprise there. So here and here. Okay, so you can see that water bodies around the planet are warming, and therefore there's more evaporation. Therefore there's more water vapor in the atmosphere. Okay, these are the warm day anomalies. So if you define the warm day as the top 10% temperatures, then these are anomalies from 1961 to 1990 in terms of the days. So look at Europe here. So in 2020, Europe had a massive heat wave. This scale here is over 40 warmer days. And the anomaly is 40 days. So 40 more days of extreme warm temperatures in Europe, and lots in Asia, and also in the U.S. Southwest and Australia. Those are the key points. If you go to, look here, this is the anomalies. This is the cool night anomalies. So you can see that these regions here they have up to 30, 20, 30, 40 days less of the year where there's cool nights. Now, cool nights are very important. When we're in very, very warm temperatures, people need the cool nights in order for their body core temperatures to lower. And the biggest stress on humans over time, cumulative heat stress, is very, very dangerous. So when we don't have cool nights for people to cool off, then the mortality rates go way, way up. This was surface temperature, okay? This is a couple meters above the ground. You define surface temperature generally about 2 meters, 6 feet above the ground. This is a lower tropospheric temperature. So this is probably something like 850 millibar a kilometer up. And you can compare these trends here, and you can see that the lower tropospheric temperature is undergoing significant warming, okay, in the far northern regions and also in Antarctica. And you can compare, so you can see that where you can still have the global warming whole area here can be seen. Okay, another thing to look at, this is a recent metric that they're just starting to look at in the BAMS report, the Bulletin of the American Meteorological Society. What you can see here, this is the night marine air temperature, and these are anomalies in the night marine air temperature. So how much is it cooling off over the oceans at night? This is the cool nights. This is over land, and this is over the ocean. And you can see that these regions here, where there's marine heat waves, you can see clearly that the marine air temperature at night is a lot warmer. So in these regions and these regions in particular. Now, surface-specific humidity. Specific humidity is a ratio. It's the grams of water vapor in the air per kilogram of air. Okay, so it's just a ratio, and you can see that there's more specific humidity at the surface pretty much across the globe, with the exception of a couple bands where the Hadley cell goes down, loops up and around and comes down. These are the regions where the deserts are in the world. Think back to the saying, wet areas get wetter, dry areas get drier. Well, these are the dry areas, and they still have a specific heat. They have a surface-specific humidity that was lower in 2020 relative to this average. And these are the amounts, but most of the globe is getting higher specific humidity. No surprise, because the globe is warming strongly, and when it's warming, there's more evaporation, so there's more water vapor in the air, and you can see the distribution here. Okay, the relative humidity is a little bit different, because now you need to take the specific humidity, you have to take this data, and what you have to do is look at the temperature rise at all the regions of the planet, figure out how much water the air can hold at every different pixel on the map, and then take that ratio of these numbers to the saturation to get the relative humidity. And what you can see is we're getting the relative humidity is drying, across lots of the land areas. So, southern South America, southwest U.S., Europe, and much of Asia. And this is very bad for plants, because there's not enough moisture in the air. So at the leaves of plants, there'll be more transpiration, more evaporation, more water loss. There'll also be more water loss from the soils. So the soils will start losing the amount of water that they hold, which can be very detrimental to the plants trying to extract water from the soil. This is the total column water vapor anomaly, and you can see that. So the total column means that if you start at the surface of the Earth and go all the way up to the top of the atmosphere, the lower atmosphere, the troposphere, and then you take all the amount of water in that region and measure in terms of millimeter. In other words, if all the water in that water column going from the surface up to the top of the troposphere was condensed and put into, how many millimeters of water would we have in that column? And this is a change in that over time. So there's the change, positive. We're getting more and more water vapor in the air columns. Okay, you can clearly see that. There's a couple areas, a couple bands where there's less. Okay, this is the upper troposphere now, the humidity in the upper troposphere, and it's a percentage of relative humidity. It's the anomalies. So, as you go up higher in the atmosphere, there's a whole mix here. Okay, some areas, there's lots of changes, but there's not a lot of order in this. I mean, you could argue maybe there's a band where there's more tropospheric, upper tropospheric humidity closer to the equator and less away from the equator. This is precipitation. These are anomalies in millimeters, and you can see these areas are getting more precipitation and these areas are getting less. And these are significant amounts, 100, 200, this scale is in hundreds of millimeters. So it's actually, but it's hard to say that, you can't really say that precipitation overall globally is increasing or decreasing. It's breaking out into different regional effects, but the overall total isn't significantly changing, as I talked about in the last video. These are rainfall anomalies in one day. Okay, this is the anomalies in millimeters. So we're not getting as much rain in these, on many of the continents, in one day, is what it's saying. I'm not. Well, there's some regions here where there's more. I have to look at this data more carefully because that's a bit surprising. Lake water levels. You can see in the areas where there's rainfall, lots of rainfall, you get positive anomalies. And in regions where there's not a lot of rainfall, you get some negative anomalies. Okay, cloudiness. This is really interesting. We're getting, this is painting a clear picture. What this is saying is that over major population centers on land, there's less and less clouds. And the anomalies are from the 1981 to 2010 climatological average. So this is in 2020. So there's much fewer clouds, and we're talking about 5, 10% in a lot of these darker brown regions. So 10% less clouds over the main continents, and there's actually more clouds over the oceans here, which is a very, very pertinent change when we want to talk about doing things like marine cloud brightening. Okay, so if you think that the sun is getting hotter in your location over the land, well, there's less clouds, and one of the reasons for this is the particulate matter. Remember, this was a pandemic year, so industry was throttled a lot of the time, and there was less particulate matter, so less cloud condensation nuclei over the land, and perhaps that's the reason why there was a big drop here. Okay, this is runoff. So runoff has, we're in regions where there's a lot more rain. If the ground is hard packed, there'll be more runoff. There's less infiltration of water into the ground, and you can see where that's been increased, and also where it's been decreased. Okay, so of course that has to relate to the total amount of rainfall as well. River discharge. So areas where it's blue are areas where river discharge is increased. Many places around the globe. Again, this is on an annual basis. And in South America, it's low. This is very worrying for the Amazon rainforest, for the longevity and continuation of the viability of the Amazon rainforest. Terrestrial water storage, way down. This is water that is stored in groundwater, etc., and it's down in these drier regions, and it's way up in Africa here, and higher in India, and high in parts of northern Canada. Soil moisture, in the brown areas, the soils are drying out, and in the bluer areas, it's actually increased in 2020 relative to the 1991 to 2010 baseline in this case. So you need to match this type of plot with the main agricultural growing regions of the world, and you can see how this coincides with like the grain belt regions and growing regions of the U.S. etc. You can see that to see how strong an effect this will have on our food supply. Droughts, they match, of course, to the soil moisture. Where there's droughts, the soil is going to dry out. So you can see where the droughts of the, huge droughts here coinciding in Europe, coinciding with the heat waves, Australia. Remember reading about South Africa, Cape Town almost running out of water, South America and the southwest U.S. Land evaporation, of course, evaporation of water from the land. I think that includes transpiration. And you can see how it coincides with the drought for the most part. Okay, not always. I mean, in Europe, there was actually more water evaporating from the land. So there's water stored in the land, soils, and evaporation increased, of course, because Europe was in a heat wave. Okay, sea level pressure anomalies. You can see areas where there was slightly higher pressure than normal, other areas where there's lower. Remember that the pressure at the surface is 1014 hexapascal. So these are small changes, but it just shows the global pattern. Surface winds, we're getting some winds. There's no clear pattern. Some areas are getting slightly weaker winds. Other areas are getting slightly stronger winds. This is the upper air, the northward component of the winds, and this is in September, October, November, December. And you can see increases in the brown areas and decreases. So you can see, if the wind is increasing in the northward here and decreasing here, you can see, that you'll be able to get sort of the pattern of the jet streams. The sort of patterns that the jet streams occupy have a big impact on this diagram. This is total aerosols. Okay, now total aerosols in 2020. This is anomalies in aerosol optical depth. So it's like the thickness of the atmosphere as light would see it. More and more aerosols, they can't get through. It's like the air is thicker for the light. The light won't penetrate through. And you can see that the aerosols are down over most of the continents. Okay, there's a couple exceptions. India, they're up slightly. Parts of Southwest South America, they're up. But over most continents, and also in northern Russia, but over most continents, they're actually down. And this is because of the shuttering of a lot of industry in 2020 due to the coronavirus. The aerosol optical depth ratio, and you can see, again, over land, it's decreasing. Over parts of the ocean and South America, Antarctica Peninsula, it's increasing. Same as Siberia. Extreme aerosol days. This is days where the aerosol optical depth is above the 99.9th percentile. So extremely high aerosol days, the number of days increase, and you can see that, I guess this is from burning fires in South America. You can see it here, and you can see a bit, well, this extends all the way over almost to Australia here. Stratospheric total column ozone. So ozone in the stratosphere, you can see, increases in some of these regions, and you could see a negative anomaly over Antarctica and over the Arctic. And the ozone hole was very, very strong in the Arctic in 2020, as you recall, hopefully from my previous video. And over Antarctica, the ozone hole was significant as well. It's unusual to have it in the Arctic. It's very common, of course, in the Antarctic. This is tropospheric column ozone. Okay, so this is stuff that's harmful in the lower atmosphere, ozone in the lower atmosphere, harmful to health. And you can see the concentrations up here in the northern hemisphere. There's a couple bands here, but it's mostly in the northern hemisphere. Carbon monoxide, this is from incomplete combustion. You can see it happening here over, near Indonesia. Okay, there's a positive anomaly. Not much change elsewhere. The land surface albedo. This is the reflectance of the land in the visible region. And you can see how it significantly was lower across all of Europe by 20% lower. Okay, this is huge. This is huge lowering of the albedo. Okay, Europe's become a lot darker. Why is this? Great question. I mean, it's there's a lot less particulate pollution in 2020 because of the virus. That would this is the surface albedo, though, in the visible. I have to really think about this. Like, why is the land reflecting a lot less light in Europe? Maybe a lot of crops that are grown have higher albedo, and because of the heat waves and droughts, there was less of them. I'm not sure. I'd have to look into this. But also lower here, and it's higher in some of these regions. Land surface albedo in the near infrared, different wavelengths. It is similar. It follows this guy. It's similar to this guy. Fraction of absorbed photosynthetically active radiation. That's that acronym FACAR, which I talked about at the end of the last video. And you can see that it's increased in some regions, especially in India. So regions, I guess, that have decent. So what it is the absorbed, like plants absorb radiation. They only absorb a certain fraction of the total radiation, and this is showing the fraction, how it's slightly increased in some regions, decreased in others. Biomass burning, as I mentioned, is way down in many places around the planet, and there are some exceptions in the brown areas. And vegetation, optical depth, so this is an indication of how healthy the vegetation is. Slightly better in the blue regions, slightly worse in the brown regions relative to the long-term averages. Now, these are temperature anomalies over the land and the ocean, and land and ocean combined. This is for 2020 with respect to the 1981 to 2010 climatological base period. And it's about 0.6 degrees for the land and ocean. Land warmed close to 1 degree, ocean close to 0.4 degrees, and 0.6 for land and ocean. And in order to put it, this is, if you look at the baseline 81 to 2010 relative to 1880 to 1910, you need to add about 0.5 on there. So if you add 0.5 degrees Celsius, you get 1.1 degrees Celsius, which is a number you probably remember as the global temperature relative to the turn of the last turn of the century. So over the last century or so. And these are some of the plots of the land and ocean increase in temperature rise. Okay, and the baseline will again be this period 1980 roughly to 2010. Okay, you can see where this curve averages, crosses zero and is averaged about zero. And you can see, so it's 0.55 up here. You can see how much the temperature has risen. This is over the land and ocean. This is just the land only. The rise, of course, is much higher over the land. It's almost double over the land than it is over the compared to the global average, and it's about half over the oceans. Okay, it takes a lot more energy to warm up the ocean. So those are all those plots. And in Europe, okay, these are warm season lake surface temperatures. So the Europe was in a heat wave, of course. So this is the anomaly of the lake temperatures. Very, very warm lakes in southern Europe, slightly cooler in northern Europe. All of 127 lakes in Europe, how the temperature trend is. In Africa, they're also warming, but not so quickly. Tibetan Plateau, the lakes up in the Tibetan Plateau are warming significantly. And in Canada, northern country, significant warming of the lakes. Okay, no surprise there. This is the lake surface water temperature and lake water level for 11 lakes in East Africa. And you can see the plot here. So the lake surface water temperature is the white trending line, and it's trending up for the most part, the white line. And the blue line is the lake water level, and there is quite a bit of fluctuation in the African lakes. This is the uptick in the number of days, the number of warm days, okay, and the number of cold days. So we're losing coldness, gaining warmness. No surprise there. And these are some of the maximum temperatures in 2020. So UK 37.8 Celsius at Heathrow Airport, Spain 36, Russia 38, US we reached that 54.4, in Furnace Creek, Death Valley, Woodland Hills, California, almost 50. Canada, we reached 36.6. Well, in Canada, this year we've reached 49.6, incredibly high temperature. Some places here. This is noteworthy, of course. In Antarctica, we hit 18.3 degrees Celsius at Esperanza Base on February 6th, and that's a new Antarctic record. There's no Arctic point here. Okay, heat wave frequency. Heat wave frequency is the blue curve, and the heat wave magnitude is the red curve. The red number is here, the blue number is here, and we're seeing, of course, trending upwards we're getting more and more heat waves April to June around the globe. No surprise there. This is global marine heat wave occurrences. So we're getting more, and there's categories: moderate, strong, severe, and extreme marine heat waves. And this is the daily occurrence as a percentage of the total ocean. This is the daily average percent of the ocean that experienced a marine heat wave. So on average, 20% or so. This number is steadily ticking up. On average in 2020, about 20% of the ocean was exhibiting a marine heat wave. This is the total percent of the ocean that experienced a marine heat wave at some point during the year. So many regions, these are much higher, so many regions of the ocean experienced marine heat waves. And this is the total average of daily marine heat wave occurrence in days for the entire ocean. So you can see more and more days the ocean is getting marine heat waves. Okay, this is the sea surface temperature anomaly in the Nino 3.4 region. It's also used as an ENSO index, and you can see that we had a slightly we had a slight La Nina, a warming period. When we have another period like the 2015-2016, then watch out. It's going to be super, super hot and crazy on the planet. This is measurement of the lower tropospheric temperatures, LTT anomalies. We use radiosondes, so radio transmissions from balloons that are tracked by radar, satellites, and reanalysis. And we're getting warming not just at the surface, but in the lower troposphere as well. No surprise there. And I'll just do a few more. This is the upper stratosphere. So global stratospheric temperature anomalies from the lower to upper stratosphere, bottom to top. So these are shifted, these are offset so that you can see them. One is added to here, 2 degrees added to here, 3 to there, just to shift all the curves so they don't overlap. And you can see the trend down here, and the slope here is much greater. So as you go higher and higher up into the atmosphere, the temperature in the stratosphere is decreasing. This is because there's less light getting up there. There's less heat getting up there. Okay, the surface of the Earth is heated up from the shortwave radiation. The heat is heating up the lower atmosphere. Less heat is going up, being re-radiated out into space. More is being trapped in the Earth's system because there's less being re-radiated up through the stratosphere and into space. The stratosphere is cooling. So this is a huge signature of climate change. We talked about on land the lowering of days of warm, cool nights, And we see a similar thing in the oceans. These are anomalies in the night marine air temperature. It's getting warmer in the marine air temperature at night. And there's some more data on that. This is linear trends in the difference between the 2-meter air temperature and the sea surface temperature in anomalies. So red colors indicate where the air temperature is warming faster than the sea surface temperature. Air temperature is taking off in the Arctic. It's warming much faster than the sea surface temperature, which is taking time to catch up. Blue colors are where the sea surface temperature is warming up faster than the air temperature. So that's happening around Antarctic. So you can see the contrast and difference between the two poles. It's quite interesting. Okay, I may as well just keep continuing. So these are, these are permafrost temperatures. You drill a hole in the ground, a borehole, and it's done in the Alps and in Nordic countries to a depth of 10 meter and 20 meter. And you measure the temperature over time, over a number of years, at that depth in the borehole. And this is a 10 meter number. So you can see there's fluctuation, but the temperature of these boreholes in different locations is all trending upward. The permafrost is heating up. It's thawing. If you go to 20 meters, the temperature doesn't fluctuate as much. Notice the scale is roughly similar, the temperature rise. I mean, you're getting temperature rise of, significant temperature rise. I mean, this guy goes from about -7 to -4. It's warmed 3 degrees since 1998 roughly or something. Okay, but there is fluctuation. This is a seasonal fluctuation year to year, but of course that's, as you go deeper, that's modulated out. Okay, that's smeared out. The temperature is more constant as you go deeper, so that's why these 20-meter deep borehole temperatures are flatter. They're not showing the fluctuations that you see at the 10-meter. This is temperature measured in permafrost boreholes on the Tibetan Plateau at 10-meter depth. And you can see again strong increases. We're warming up the planet, we're warming up the ground. This is the active layer thickness in centimeters. So the active layer is the layer that thaws and freezes, thaws and freezes. And you can see that the active layer thickness is increasing, and the air temperature, it's tracking the air temperature anomaly very closely. Rock glaciers are being monitored. Okay, these are glaciers where, instead of, there's lots of ice, but it's predominantly rocks or rocks on top, a big mixture of rock and ice. And you can see that the velocity of these is increasing significantly since the 1990s, increased to 2000, notching up even more. And these are a good indication of the warming regions. Now this is the 12-month running anomalies of monthly snow cover extend over northern hemisphere lands as a whole. Okay, we've got northern hemisphere is the black line, Eurasia is the red line, and the blue line is North America. And you can see the trend to, in 2020 we had a very, very low snow cover over the land. This would greatly increase the albedo of the land, greatly increase the amount of sunlight absorbed, and cause the temperature heating anomalies. And then you can see the month. This is the snow cover. This is northern hemisphere continental snow extent between November 66 and December 2020. Areas are in millions of square kilometers. Okay, so this is by months of the year, and you can see that snow cover, in the spring, way down. July and August, way down. This is the annual average in millions of square kilometers. Okay, so we're losing snow cover. It's causing the Arctic to greatly warm. This is the mass balance of alpine glaciers in millimeters of water equivalent. Okay, and this is what you can see. This is the mean specific annual balance, so loss of water equivalent, 1 meter water equivalent, and then the cumulative amount over the years. And for 30 odd years, we've been continuing to get strong loss of glacier ice. This is in the alpine regions of the world. Okay, the high elevation regions. Okay, this now, if you look at the ice formation on lakes, when the ice comes on, okay, this is the anomaly in days. So the ice is coming on lakes at later and later dates of the year, and the ice is leaving lakes generally at earlier and earlier dates of the year. So the ice duration is decreasing significantly, and this shows you the loss, 20 days loss of duration in the year of ice. Okay, again, this is in 2020 relative to the long-term average. There's some lakes here that, where it's been colder in this region. This is the air temperature. You can see the lakes are just being hammered, of course, no surprise there. Start of ice cover, it's getting later and later in the fall. Okay, and the end of ice cover is getting earlier and earlier and earlier. So the duration of ice cover from these two curves is decreasing significantly on lakes. This is the Great Lakes in Canada. You can look at the the Great Lakes and the different colors of the different lakes, and you can see how the general trend is the maximum ice cover anomaly percentage is decreasing here. So less and less of the Great Lakes are being covered with ice. This is specific humidity trends and relative humidity trends. Okay, specific humidity is here. So again, over the land, over the ocean, we're getting higher and higher specific humidities. There's more water vapor in the air. Over the relative humidity, however, is decreasing because the temperature over the land is increasing. So the saturation level, the amount of water vapor to saturate the air is increasing, and it's increasing at a faster rate than the specific humidity is increasing, so the ratio is actually decreasing. And this is very bad for plants, as I've pointed out before. Total column water vapor increasing over the ocean, increasing over the land. Okay, and we know why. I've talked about it. This is the total column water vapor anomalies as a function of latitude. So there's more and more water over the land areas, over the surface of the Earth in general. We're going, as we go through the years, we're getting more and more blue, more and more water, total column water vapor, because we're in a warming planet, rapidly warming planet. And this is the upper tropospheric humidity. Not too much change here. I'll just go to a few more here. This is the globally average precipitation anomalies in millimeters per year. So there's not much change. Okay, this is the land. This is the ocean. This is over the globe. There's not too much change. I mean, you could argue a slight upward trend. If you did a best fit line, this is a zero line. If you did a best fit line, more of the curve is above the line than below in this region here. So you could argue maybe a slight increase in global precipitation, but not too much. And this is the number of heavy precipitation days, decreasing here, increasing over a lot of the land areas. And those plots I won't delve into that too much more. This is the lake water level time series of different lakes, and you can see, Caspian Sea decrease, the Aral Sea is just about disappearing. Lake Superior was dropping for quite a bit, increasing. Okay, so there's different. So since over the last almost decade, not quite, the Great Lakes have been getting more water before people were worried about them completely going much, much lower. Indian Ocean dipole. This is global seasonal cloudiness anomalies. This is very important. This is December, January, February, March, April, May, June, July, August, September, October, November. So what we're seeing is over the land, we're getting fewer and fewer clouds in general for most months of the year, not so much in the summer. Okay? And over the oceans, we're getting more clouds. So this is very interesting global phenomena. Over the oceans, we're getting more clouds in general. Over the land, we're getting fewer. And over parts of the land, we're down, we're getting 5, 10%, even 15% fewer clouds. So the land, this is contributing, of course, to the land warming much faster than the ocean as well. Indian Ocean Index, I'll just keep going. I won't talk about everything here. Terrestrial water storage, soil moisture, drop off here, increase, but there's a lot of fluctuation depending on the rainfall, etc. This is the percentage of global land area with drought, moderate drought. Okay, the lightest color, severe drought and extreme drought. So we're seeing, we saw an uptick here of extreme drought in 2020. Changes in categories from dry areas are the brown, wetter areas are the blue. Land evaporation, and so on. Okay, so I think that's enough. I'm kind of worn myself out, probably you too. Anyway, download the report, high resolution PDF document. It's called State of the Climate in 2020, BAMS. The online version just came out on August 25th, less than a month ago, and it's chock full of great information on changes in the climate. Again, thank you for listening. Please check out my website, paulbeckwith.net, and consider donating to my PayPal for my efforts. Again, thanks for listening and have a nice day.